Good morning, students. So in the last class we discussed about the different concepts regarding our electric dipole and that of dipole field. Now our concern is about a basic part, that is called our electric field lines. So see, I gave a brief introduction in the last class that if we want to see or want to imagine any structure, if I will write the name only here, and if you know the structure, like I wrote in the last class, that if I will write mango, then you can easily imagine, you can easily visualize how a mango looks like, so that there is no concern about showing you a mango here. The same way, when there is two electric charges, let us say plus Q and let us say minus Q, they are attracting each other due to the dissimilar charges. And if I will place a plus Q here or minus Q and minus Q, they will start to repel each other due to similar nature of charges. So the question arises, as already we studied, that around it there is a space which contains its electric field. There is a space which needs electric field. But we are not able to see the electric field with our naked eye. That's why what we did, like that we imagine that there will be some lines or curves in between two charges due to the electric field, and those imaginary lines or curves are called your electric field lines. So this is a particular imaginary concept. There is no proper presence of these lines anywhere, but for our clearance of the concept, for the theory to satisfy, we took that there must be some imaginary line or curve which is helping us to describe the electric field inside two charges. So there are different cases are there. If you will take isolated charges, that means a single positive or a single negative, that means a monopole if you will take, then how the lines of forces will go through it. And when we will take two dissimilar like plus minus or minus plus, how the lines of force works. And if you will take two similar nature like plus plus or minus minus, how those lines of forces are being represented. So this is completely a pictorial notation. We are going to draw a number of pictures here, that how lines of force are going to represent the electric field in between pair of charges in your isolated one. So at first we need to write the definition, then we will go for some properties of it, then we will draw the diagrams. So if we will write the definition of it, we can write these are imaginary lines or curves. At any point if you will draw a tangent, then at that point we can easily calculate the electric field intensity. Okay. So if you get the definition, it is an imaginary line or curve where a tangent drawn at a point represents the electric field at that point. Or another definition, that is electric field is a path where a unit positive charge would move if it is free to do so. So these are two definitions. This one is the proper one. Always remember, you need to read this definition every time. It is an imaginary line or curve. See, it is a line or can be a curve. Must be in one-dimensional structure, where a tangent drawn at a point represents the electric field at that point. So like for example, if I will say okay, so if you will discuss about this at first, then see this one. E is a path where a unit positive charge would move if it is free to do so. Like for example, let us consider, if I am going to place, let us say this is one line of force. Clear? That it is started from plus Q, let us say it ends at minus Q. Always remember the lines of forces started from positive charge and ends at negative charge. So if I will place, let us say, a unit test charge of positive nature, then what will happen? This plus q will start to repel this one along this direction, and this minus q is going to attract this one along this direction. So this plus q will start from here due to repulsion from plus q and will go in a path. We don't know the path. The path will be described by this one only. Go in a path by the attraction force of minus q. So the repulsion force from plus q and attraction force from minus q is going to define how this unit positive charge is going to move in a particular path. So this path now from plus q to minus q, where this unit positive are going to move, is called your lines of force. So this is the basic condition for the second definition. Now we will go to the first one. So let us consider we are having a positive charge. Let us say we are having a negative charge. By sign convention, always moves from positive and reaches a negative. So let us consider I want to calculate what is the electric field at this point. So what will happen? See, let us say if I will going to place a unit positive charge, let us say positive one, then this will repel this one, this positive charge with a higher value, let us say E1. At the same time, the negative charge is going to attract, but as the distance is more, so the electric field intensity is found to be less. So at this particular point, due to positive there will be a repulsive electric field, due to negative there will be one attractive electric field. So as two electric fields are acting simultaneously, this will give in the form of a resultant. So if I will say now what is the direction of electric field at this point, then we can get the resultant as the electric field. So this is the basic part. So this is the direction of electric field. So this is the basic case. Imaginary line or curve where a tangent drawn at any point represents the electric field at that point. So in this way here also the same thing will happen. Here what will happen? This will become less, this will become more. So you will get electric field here. So in this way the resultant of the two effects of electric field on any charge due to plus and minus is going to define the direction of electric field on those points. So this is the basic expression or the description for the definition of your electric field in case of electric field lines. Clear? You need to remember both of them. Understood? So now we will go to the properties. See, there are many properties are there. From that 4 5 are quite necessary. So in your board exam there may be a short note. What is one? You need to write 2 or 3 properties. So let's write down properties of electric field lines. Clear? Okay. First one is they always starts from positive and ends at negative. These are continuous curves. In magnetism you will get continuous curves as well as you will get a loop form, but here you will only get a continuous curve. Like for example, if I will take a positive charge here, let us say a negative charge here, then from positive to negative this will go, from positive to negative this will go. You need to specify the direction. And here also always lines of force are coming out from the positive, coming out. Always lines of forces going in towards the negative, so it will be going in. So this is the particular pictorial representation. How the lines of forces, see here it is curved. If you want to calculate the intensity, you need to draw a tangent only here. Then you can see that in this place the direction of field is this one, and you can easily calculate the line angle also. So from plus to minus the lines of force is moving. From plus it is coming out, negative it is going in, and it is seen. They are completely continuous curves. There is no discretion, there is no breaking. So from positive the lines of force will start, they will end at the negative one. So this is the first case, that the when you will take any lines of force, it always starts from positive and it will ends at negative. So now the question arises, if there will be no negative charge, only a positive, that means I can say the isolated positive charge, then what will happen? The lines of force will come out, it will go to infinite. And if there is only negative charge, then the lines of force will come from infinite and will end at the negative charge. We will draw the pictures after this. Clear? So this is the first property. Lines of forces always starts from the positive and ends at negative. These are continuous curves. What is one? You need to remember this one. And always remember that here also you can write, they don't form continuous loop. See, continuous loop means if they will go like this and if they will again return like this, then that is going to form a continuous loop. But here from negative to positive, there is no motion of the lines of force. That's why it is only a continuous curve. It is not a continuous loop. So it is the difference between electric lines of force and magnetic lines of force. In magnetic lines of force, what you will get? If this one is, let us say, north pole, this south pole, from north to south the lines of force will go, and from here to here the lines of force will come. So they are forming some closed loop. But here this is not possible. So this is the only difference between your lines of force of electric field and that of magnetic field. Clear? Okay. Now we will go to the second one. Okay, the second property is that is saying electric field is a real quantity. Clear? Because it can apply force on charged particle and move them. So see, let us consider I am having electric field like this. Here is a charge. So that electric field will come like this. It will strike the charge. If this electric field has an effect, if this is a positive charge, then this electric field either can push it or can pull it. So one electric field whom we cannot see, it comes in the form of a lines of force, but it can have the capability to push or pull another charge. That means it is applying some force. And we know that if we are going to see, like for example, the object is here, you start to push it with a force, so the object displaces. So for the displacement of this object, you need to apply some force. So the same thing is happening here. As we are not able to see the electric field, still the electric field is able to put one effect. Like this, the electric field is coming like this. There is a charge. The charge is going to hit by the electric field, and depending on the nature of this electric field, this charge is going to be repelled or be attracted by the structure. That's why as the electric field is have the capability to put one effect, either repulsive or attractive effect on any kind of charge. As we are not able to see it, still electric field is considered to be a real quantity. Always remember this one. This is quite necessary point. Got this one? That means physically the charge is going to experience some force, some effect. That's why it is considered to be a real quantity. Got this one? Then okay. Then we will come to the third one. Field lines starts from positive and ends at negative. Already we have discussed about this one. So this is the another point. Clear? Okay. Then the fourth one is tangent drawn at any point gives the direction of electric field at that point. So already we discussed about this a bit. Like for example, you are having a positive charge here and you are having a negative charge here. Then from positive to negative, the lines of forces are moving like this. From coming out, and 2 negative, it is going in. Then let us say I am going to place a unit positive charge here at this point. So what will happen? This positive charge is going to repel the unit positive charge with one electric field in this direction. Let us say E1. At the same time, but as the unit positive charge is near to this positive charge, so the effect of electric field in the form of repulsive force is going to be more. That's why the tangent I have drawn is, the length is little bit higher. Negative one, as it is at a higher distance, so the electric field on it is found to be less. So when on a particular point, let us say point A, 2 electric fields are acting due to positive and negative charge, then it must have a resultant. So this is the direction of electric field. That's why this is the way how we can easily define what is the direction of electric field at any point when you are talking about the lines of forces from positive to negative. So this is the basic part. So tangent drawn at every point gives the direction of electron at that point. So instead of going to this one, you can only normally draw a tangent also, that can be also helpful for you. So this is the 4th point. Then the 5th one is quite necessary. Like for example, if I will ask you that is it possible that I am teaching you now and also at the same time I am teaching at somewhere else, so it is not practically possible. Got this one? The same thing is happening in the next concept. It is saying that no 2 lines of forces, can intersect each other. Always remember this one. So they cannot intersect each other. No 2 lines of forces. So the question arises, why? Let us consider you are having a line of force here. Let us say this one is 1, 2. Let us say this one is 3, 4. Line of force. So for example, for these 1, 2 lines of force, if I want to calculate the direction of electric field at this point, then what I will get? This must be the tangent I need to draw. Let us say this is E1. At the same time, if I want to calculate the direction of electric field for 3, 4 at this point, I need to draw a tangent here. Let us say this one is E2. So see, on a single point at a time, there is direction for 2 electric fields, which is quite impossible. Like for example, you will say that you are at Sunabada and at the same time you are at Koraput. It is not possible. The same thing is happening here. For this particular point where they are going to intersect, at this point the electric field for this common point is found to be 2 directions. That's why, which is not possible for a single point. That's why 2 lines of forces can never intersect each other. If they will intersect, then there will be 2 directions of electric field on that particular point, which is practically impossible. Got this one? Okay. Then the next point comes, like for example, there is a tunnel and I will say you that you need to walk. And if from the other side many people are coming, like for example here, let us say you are going in a, let us say structure, you are moving from here, and from here a bunch of people are coming. What is this one? A bunch of people are coming. So when you will start to move from point A to point B, if the number of people density are going to be very higher, then it will be very difficult for you to cross them. That means you can say in a rush, in a crowd, it is difficult to walk. But if the number of people here are very less, let us say, then what you will do? Easily you can cross. That means you can say in a spread out, in a empty space, in an empty place, you can easily walk. But the same thing is happening in case of lines of forces also. Lines of forces are of 2 types. It can be crowded or it can be spread out. When I am saying crowded means in a small space, if the number of lines of forces are higher. Like for example, so next point, the 6th one we can write relative closeness of field lines gives the idea of strength of the electric field. That is crowded lines of forces represents strong electric field. I'll remember this one. So, like for example, if I will say, let us say here I am having lines of forces like this. They are very near to each other. Let's say here I am having lines of forces like this. We will discuss about this concept again in our electric flux. So if I will place any region here and if I will place any region here, then the number of lines of forces, let us say this one is also 1 meter square, this one is also 1 meter square. So here in 1 meter square you are getting, let us say, 2 number of lines of forces. Here you are getting 1 number of lines of forces. So the lines of force always represents, always going to prove what is the field strength or what is the strongness of electric field. So if the lines of forces are going to be crowded, they will always give you the idea about the strong electric field. If they are spread out, it always gives idea about the weak electric field. So the number of lines of forces, which is also called as flux. Next we will read about them. Got this one? So number of lines of forces in a particular region, if is more, then that represents the strong electric field at that position. If number of lines of forces are less in a particular region, that represents that the electric field intensity will be weak on those positions. That's why crowded lines of force represents strong electric field, whereas your spread out lines of forces represents your weak electric field. So these are the basic properties of your electric field lines. Now we will go to the pictorial representation of electric field lines. Write down. Pictorial representation of electric field lines. First one is for isolated charges. So first one is, let us say I will talk about one isolated positive charge. Then we know that always lines of force coming out from positive charge. So that lines of force here also will come out from positive charge. Come out from positive charge. You need to give the direction particularly. Come out from positive charge. That is the come out from positive charge. Like this. In all directions. I already discussed about this one. Clear? For a charge, for a point charge, this is a point charge. Then the radial formation of electric field will produce. That's why this, you will add them. You will get a circle of radius r. We already discussed about it in our concept of electric field, point charge. What is some radial field? At the same time, let us say you are going to take a negative charge here, isolated one. Then we know that always the lines of force are coming in. These are the lines of force coming in. Like this. These are the lines of forces. That means when they will start from here, they will end at infinite. Infinite means at a large distance somewhere there will be a negative charge. And when I am talking about this one, infinite means there is a large distance. Don't think that they will come from infinite somewhere else. They will come from alien Mars or somewhere. It will be from infinite means at a larger distance. They are coming and they are going to enter in the negative charge. And they are coming out and going to the very larger finite distance. It's not like that we will go to infinite only. The distance is too large. Got this one? So these are the diagrams for your isolated charges. Now we will go for the pair of charges. So two cases will come. One will be pair of charges for similar nature. One will be pair of charges for dissimilar nature. So in case of dissimilar nature, what will happen? They will start to attract each other. That means the lines of force which is emerging from positive will be attracted by negative one. But in case of your similar charges, they will repel each other. So second one we can write for pair of charges. Let us say we are having dissimilar charge first. What will happen? Plus to minus, it will go from plus to minus like this. It will come from plus, coming from plus, entering at minus, entering at minus. So this is the diagram, like this way. From positive it is coming out, to negative it is going in. That means if I will draw a larger one, then also the lines of force will come like this. From positive it will come out, and negative it will go in. So this is for your dissimilar charges, or you can say unequal. Got this one? Here if you take, let us say, positive and positive. So the line of force will come out from here. It is being repelled by the positive. It will change its path. The same thing, lines of force will come out from here, repelled by the positive. At the same time, lines of force will come out from here, repelled by the positive. Come out from here, repelled by the positive. The same way will also happen. It will be repelled. It will be reversal. So this is the diagram of lines of forces. Got this one? And also you need to remember that for uniform electric field, the lines of forces are always parallel and equispaced lines. Got this one? This represents your uniform electric field. So these are the representation of your isolated and pair of charges in the form of a picture. So you need to be very much clear about this concept, then only you can understand. And also there is a case that we already discussed in case of your line charge distribution. We draw that if it will be, sorry, in case of your surface distribution, if it will be like a plane, then always lines of forces are coming out. So for a conductor, this can also be one diagram. Got this one? For a particular charge plate conductor. What is a charge plate conductor? So these are the basic concepts of your lines of forces for your isolated and pair of charges. Then the representation of uniform electric field, and also for the plane one. So this is the basic case of lines of forces. So up to this, with this lines of forces concept is going to